Okay, so this is what we have been doing. Some work that is very computational, and we're just building up tools so that the life is easier. So one is right there at the top, the product rule for differentiation, but at the same time let's apply it a few times, and then we'll get just a bunch of functions right away that we will know how to differentiate, and we won't have to go back and forth and look at the limits or even the rules of differentiation. So as you can see, we haven't been doing limits anymore. So we will have only the rules of differentiation. These two we'll have more. We have the derivatives of some basic functions, such as the linear quadratic function, derivative of sine cosine, and it's the exponential function. Okay, and now we are expanding it to power functions. All the power functions are here. The pattern has become clear, right? Remember this last time, and indeed we could write now the nth power, the derivative of the nth power will be what? According to the pattern that we have discovered, this is the pattern. So the
n times x to the n plus 1.
X n minus 1. So the power goes down. This is called the power formula. Okay, and the power goes down. When you have power function, it always goes down under differentiation, and but not too far. So if we want to be specific, we would have to say n is equal to 1 and only integer values. So only the integer values are allowed so far, but we can try to extend it. And what if we differentiate 1 over x? 1 over x, I don't think we have differentiated it, but so if we are to differentiate it, let's h goes to 0. Let's differentiate 1 over x, because what's 1 over x if not another power function, but this time it has a negative power. So we have positive integer powers so far, and we discovered this pattern. Now we can differentiate any function. In fact, we can differentiate any polynomial as well. So not only every power, but also every polynomial. But 1 over x, just to expand it beyond, this is what we have. We have 1 over x plus h minus 1 over x over h. We did something like that, but let's run through this one more time so we get the whole thing. So common denominators will have h here. In the denominator, I'll have x plus hx. What's the numerator? X minus so you multiply the first fraction by the second denominator. That's how I got x. Then you multiply the second denominator by the first numerator, or the second numerator by this by the first denominator. So it will be x plus h. Okay. Okay. So that allows us to cancel x as always, and we're left with h, which can now be cancelled. So we're left with what? Negative h over x plus hx divided by h. Okay, and then h is gone, and we are left with a limit of negative 1 over x plus hx. Okay? What is this limit equal to? It goes to 0. X not equal to 0 naturally. So, negative 1 over x squared, yes. Negative 1 over x squared because 1 over x is continuous for x not equal to 0. So we get the whole derivative right away. Wherever the function is defined, it is continuous and it is differentiable. And actually what I meant to say here is, it's not that 1 over x is continuous. It is this function is continuous. This function is continuous with respect to h for h naught, something like that. X not equal to negative h. Okay, so it's a function with a fixed x, function of h, so over, it is continuous over h, and as long as that h is not equal to negative x, the function is differentiable because that way there is no division by 0, and then we can substitute, which is what we did. Okay, so the last step is to realize that we're looking at a power function. What is it equal to? Negative x squared as a power. No, there's a division here. I don't want a division. What do I do with powers when they are in the denominator?
Just bring it up top.
Yeah, so what do I get? Here.
Is it positive?
No, it's still negative. No, it's still negative. Negative remains. So 1 over x squared is equal to x to what power?
The second.
Negative.
Or negative 2.
So the power, when you bring the power, then when you bring the denominator to the numerator, the power becomes negative, and vice versa. Okay, so that's division is negative power, just the way I did it over here, right, in the beginning. 1 over x is x negative first power. Same story. So anyway, so that look it up if you were not comfortable entirely with the powers. And then we realize that this is a power function again, but with a negative power, and it fits into the pattern of the power formula. Okay, it's still, so we're trying, if I take my power formula and plug in n equal negative 1, look at what happens. X negative 1 prime is equal to negative 1 x negative 1 minus 1, which is exactly negative x minus 2. Okay? So it is confirmed then that it works. So the power formula works not only for these, but also for plus or minus 1, plus or minus 2, all of the integer values. It usually is not, you don't say that it is equal for n equals 0 simply because then you'd have a division by 0. Derivative of 0 is 0, so that's it. So, but as far as the all integers other than 0, the formula applies. Okay, so if that certainly is a conjecture, we don't want to go into the whole proof, but you can certainly look it up, and there you go. You have covered all the integers. The next step would be what about rational? Rational powers, such as x1 half. So does the still formula apply? So it will be by the power formula, we would have 1 half x 1 half minus 1. Okay? Or, well, so that's if it is expressed as a power, so it will be 1/2 x negative 1/2. Okay? So, okay, so another thing that you need to know about powers. What do we do with fractional powers?
Square root.
Square root, that's right. So there you go. So the question is actually what's the derivative of the square root, and we can work it out in a similar fashion. Just don't want to. I will write the first step, but then we did something like that not long time ago. So that would be the formula to work out. You might even remember what the trick is. How to remove the indeterminate expression here. It is 0 or 0, right? Remember what the trick is we used some time ago? Multiply by the conjugate. Multiply and divide by the conjugate. So it would be limit x plus h minus x. And then I multiply by the conjugate of this, so x plus h squared root plus square root of x. And here I still have the same thing. So long story short, it works. Okay, and so the answer, once you go through all the computations and simplifications, you will end up with 1/2 square root of x, which is same as this. Okay, so same. So rephrasing powers as rather it works the other way. In fact, more than the direct. So if you see roots, you rephrase them as powers, and then use the power formula. Okay. So for example, if I am to differentiate, not like this, but if I am to differentiate, say, cubic root of x to the 5th. How do I differentiate this?
You're still doing the difference quotient, right?
No, I don't want to, exactly my point, I don't want to do this anymore. I have my power formula. So the power formula is x. Let me put, say, p here. Prime is equal to px p minus 1, and p is any rational number. Okay, so that's the power formula we're going to be using. It's, in fact, will be even further improved. But any rational number, including negative, including fractions. So the idea is, that's what you should know even before you get to use the formula. You should remember that all the roots, as well as divisions, will give you, if you know how, will give you powers. Okay? So I want to convert, then to apply the power formula, I have to convert this into a power, this one.
X to the 3/5.
X to the 5/3. So the power is to the 5th, that it remains there. It's when the root is, it becomes the denominator, okay? So then my p is equal to 5/3, and I apply the power formula. As you can see, that power becomes the coefficient in front of the function, and then the power of the function itself goes down by 1. So it will be 5/3 minus 1. Okay, so in other words, we have 5/3 x 2/3. Okay, so it is a serious shortcut, and we did not have to do this. So this is certainly can be done, and you should be able to handle some of the simpler cases than to do differentiation from the definition. That is a typical problem on all kinds of exams. Yeah.
So that's in the derivative.
This is the derivative, yes. And all we have to do is to apply the power formula. We didn't have to do the difference quotient. Okay. So furthermore, there is the even better version of this power formula. It is actually applied to all reals as well. So let's just say p is not equal to 0. Okay, all real numbers, doesn't matter. So for example, x to the pi x pi minus 1. Okay, there, the whole thing. So the formula is simple. If you apply it a few times, you'll find it simple. The conversion, however, might if you haven't done enough of it in the past, that might take a longer time. The conversion of functions with roots, with division, and so on into power function, like we did over here. So this is to put the formula into a more convenient form so that you can apply the power formula. Okay, so this how did we get from rational numbers to real numbers is from rational to real. Maybe you remember the discussion, how you how you move from rational numbers to real numbers from early in this course.
Can you multiply by the reciprocal?
No, that's not what I had in mind. What I meant in mind, I mean, you cannot, first of all, what is a number that is real but not rational? It's called an irrational number, by the way. And the pi is a rational number, but also square root of 2 is a rational number. What is that make them irrational? They cannot be represented as a ratio. So 2/3 is not 1/3, it's not 2/3, it's not 3/2. So there is no fraction that represents the square root. Okay, so that goes all the way back to ancient Greeks. They discovered that. So they build a square one by one, and they thought all the numbers are rational, and then they discovered that the diagonal is irrational. Okay, that was quite a shock. So they thought that the numbers came from God, so they have to be meaningful, and they little nice fraction. Everything is a fraction. That was perfect. But then they proved mathematically that square root of 2 is not a rational number, and then there you go. So then how we learn early in this course to handle numbers like this. What do you do with the square root? How do you handle it?
The 1/2 power?
No. You approximate. You approximate irrational numbers by rational numbers. So, say pi is approximated. Remember, 3, 3.1, 3.14, 3.141. Okay, so that's an approximation of numbers, and that sequence of rational numbers converges to pi. Same with the square root of 2. So you can use any decimal representation in particular to find an approximation of an irrational number. So if we can handle differentiation of functions that are for rational powers, then we can also handle the irrational powers as well if we just carry out this transition properly. It's a little bit far-fetched because it does involve some more advanced steps, but let's just accept that this can be carried out, and that's how we switch from first of all, that you need this to begin with. You need to, how do you even compute functions with like x to the pi? How do I compute it? That's how. Oops. X to the pi is computed according to this limit over here. So x3, x 3.1, x 3.14, x 3.141. Okay, so that sequence of numbers, what does it converge to? X to the pi. Okay, so that's how we create functions with irrational exponents or powers. Okay, so and then once we do that, we need to justify that each of these are subject to the power rule, and then we conclude eventually that we can justify also the same formula for the irrational powers as well. And so any real number can be then subject, we can have a function with power that any real number, including pi, and all they all satisfy the same formula, the power formula. Okay, so we can't really avoid irrational numbers. Remember that they are everywhere. So if you take an interval of between 0 and 1, you have a lot of rational numbers. They cover the whole thing, but there will be a bunch of gaps. So if you want to study kind of a continuous space, continuous time, then you got to hit a lot of irrational numbers as you move from point 0 to point 1. Okay, so then the idea is what we have already learned is that we can differentiate polynomials with these rules. Not too many. So say 3x to the 5th minus 7x to the 4th plus x squared minus 7. And then you just split it and apply until you only end up with the with powers, and then apply the power formula. Okay, so I first split them into according to addition subtraction. So I'll have these are the last operations carried out with this function. Okay, and then I factor, so that's the sum rule. Then I apply the constant multiple rule to factor out those constant multiples, such as 3 and 7, and well, nothing here. And I can also observe that this one is in fact 0. Okay, so that we don't have to worry about that with the derivative of the constant. Okay, and now I have my power for formula finally coming into play, and I have okay, so carefully, especially if you for early on when you doing power formula, identify what R is. Write the formula next to you. Say once again x. Say R prime is equal to R xr minus 1. In each of these cases, identify what your R is. R is equal to 5. R is equal to 4. R is equal to 2. Okay, and then apply the formula. So look at the right hand side. So I'll have 3 times. And in parentheses, I have 5x 5 minus 1. Okay? Minus 7. R is equal to 4, so it will be 4 times x 4 minus 1. And then the last one is simply that one is familiar, but let's do it anyway. So it will be 2x 2 minus 1. Okay? Well, you just simplify, and you have 15x to the 4th minus 28x to the 3rd plus 2x, which is the answer. Okay, so we only apply the 2 basic rules here as well as the power formula. Okay, so but we already had a new rule. A new rule of the third rule was the product rule. Where is the product rule? Where is the product rule? Here it is, the product rule. Okay, so both functions are naturally differentiated. That's the point, after all. But the functions themselves also reappear. So you multiply the derivative of the first function times the second, and then the first function times the derivative of the second. Okay, so it's a cross multiplication. So if you are to compute any kind of let me do this example. Say I'm differentiating sine x. Or did I do it last time? Maybe. I guess not. So I applied the formula to do the power formula to find the power formula, but I could just as well do this. Okay, so if I need to compute this derivative, how do I do it? I could write it out, the 2 derivatives separately. So sine x. Okay, if derivative is cosine x. Okay. And derivative e to the x is equal to e to the x. Okay? So, and then I still have 4 functions. I have four functions in these two lines, and now I cross multiply them, right? So f prime g, f prime, so this is f, and the other one is g. So f prime is here, and this is g. Okay, that's the first term of the product rule. And now the second one is f, which is this, times f prime, g prime. Okay, so in the, like I said, it is a cross multiplication followed by addition. So let me carry that out. So it will be so f prime cosine x times e to the x, okay, plus the other two, sine x times e to the x. Okay, so that is the derivative. Two functions involved. Also differentiate them. You have four functions. Cross multiply, add. You have the derivative. Okay, so that's roughly how it works. And once again, remember the meaning of the meaning of the formula is to express the rate of growth of a rectangle, the area of the rectangle in terms of the growth of the two sides. That's at the top, see over there. So that's what we're looking at. Okay, so there is one more formula. That's now we have division. So it's slightly more complicated. So let me just write it out. Quotient rule. A quotient rule is similar to, it looks similar to the power rule. I'm sorry, the product rule, but it is a fraction. So both, under these conditions, both f and g are differentiable at, say, x equal a, and we don't want to divide by 0, so g of a is not equal to 0. Okay, so we're talking about differentiability at one point. If both of the functions are differentiable, then f over g is differentiable at x equal a, and the formula holds. Okay, so don't forget the fraction, but the numerator, as you can see, of the quotient rule looks similar to the rule for the product rule, except you have minus instead of plus in the middle. Okay, so you can apply, for example, to find the derivative of tangent. So tangent x prime is sine x over cosine x, right? So once again, early on, if you are doing it for the first time, identify the functions before you apply the formula, so that way you and find the derivatives in order to, so less likely to something that will go wrong. So I write f is equal to sine x, and its derivative is cosine x. Okay, and then g is equal to cosine x, and its derivative is negative sine x. Okay, so these are the four derivatives. Once again, they appear in the numerator as a cross multiplication. Okay, so starting from top right, so careful with the order. So you have multiply cosine times cosine, and then you multiply sine by negative sign, like this. Okay. That's what this is. Let me circle this. So once again, the first term is this, and the second term is that in the numerator. Okay, so that's uncomplicated. So The order matters, right? In the product rule, doesn't matter which one comes first. Here, it does matter, so it will be cosine x times cosine x and minus sine x times negative sine x. The denominator is cosine squared x. Okay? Let's simplify. So it will be cosine squared x plus sine squared x over cosine squared x. How do we further simplify this? No, you cannot just divide in that manner, because then you would have to divide sine squared by cosine. You can only divide if you split the fraction into two. No, there is an easier way to simplify it.
Don't they all turn into something? They're all interchangeable.
They're all interrelated, is what you're saying. All trig functions are interrelated, and there are a bunch of formulas that will simplify things. But what I'm asking you to remember is the very simplest, the very first trigonometric formula that simplifies things for the numerator.
Doesn't cosine squared x plus sine squared x equal 1?
Yes. So, yes. And what's the name of that result? Cosine squared plus sine squared is equal to 1. No, there is. Go back. Well, this is my picture. So the angle is x, okay, and then this is cosine x, and this is sine x. Okay, so if the angle is x, and the hypotenuse is 1, then the one of the sides is cosine x, and the other one is sine x. Okay, so then what's the meaning of the formula we just applied? This formula. It's the Pythagorean theorem, yes. By the Pythagorean theorem, that's the number one out of 100, seemingly, formulas of trigonometry. Okay, so the rest you might forget. This one you definitely should remember. Well, maybe a couple more, but that's the main one. So all trig functions can be differentiated, and it is really an arbitrary way to any function you plug in, as long as you know the derivative. So the functions involved, you can differentiate them. You can combine them through these 4 operations, and you easily get the derivative of the result. Before we move on, I want to write these properties one more time together and using the Leibniz notation. So rules of differentiation in Leibniz notation. So, for example, the point of Leibniz notation is often it gives you the ability to skip over the names of functions and rather concentrate on variables. Okay, so for example, that's a little bit harder to do with Lagrange notation. So we have y is equal to y of x. Okay, for example, that would be the main thing, is that the name of the variable of the other variable, the dependent variable, is the same as the name of the function.
Leibniz?
What?
Is it Leibniz notation?
Leibniz, with a Z, Leibniz. So, and then that saves you some work in trying keeping track of things when you have more than one function involved. Then you might want to name the variable by the name of the function, or vice versa. So anyway, this is how it works. I differentiate the sum, and I already did this last time, but let's do one more time, a slightly different way. So is the y a function, or is u a function, or is it a variable? Or is v a function, or is it a variable? It doesn't matter. It doesn't matter. As you can see, what I have on the left, you can have both ways, and just use whichever is more convenient. So that's the sum rule, with minus possibly. Constant multiple rule, I differentiate with respect to x as c function of u, and I have c du dx. Okay, so the notation emphasizes, especially those parentheses, emphasize the differentiation step, differentiation as a way to process functions. So in parentheses, you see you have a function. It is unspecified, which is good news, because the rule applies to a bunch of functions at the same time. So and then on the other end, what comes out is a new function. Okay, so the left-hand side is the that function of functions, and on the right is the output of that function. And these are just rules of how that thing works. Product rule: u times v du dx, v plus u dv dx. Okay. Quotient rule, slightly that one, this becomes cumbersome in comparison to the original. Okay, so there will be only one more rule to make it complete. So these are technically not rules. Once again, remember, these are not rules. These are just the formulas of the rules. So from those rules, we extracted the formulas to put them together in the shortest possible way. But there's always the build-up is how we the differentiability that we have to require for all of these functions. Okay, so there is really no challenge then to differentiate, like I said, any function you can imagine. It takes just some practice. If you've never seen this before, it takes some practice to get used to apply this formula. It's like algebra that you have known, algebra of powers, exponents, and so on, that is applied now on the next level. It is algebra of functions rather than numbers. Okay, so look on the left. Once again, we process functions. We don't process numbers anymore. So each of those little symbols is in fact a function. But function is arbitrary function as long as you know their derivatives. It works out pretty easily. Okay, so the story doesn't end here. And one is what we did last time is you can continue differentiating a function. Okay, so that's what we did. If you remember sine x, if you differentiate, you got cosine x. If you differentiate one more time, you have negative sine x. Okay? Let's differentiate one more time. We'll have negative cosine x. And what's the next one? Sine x again. So a full circle. So differentiation is allowed to continue as long as the function is still differentiable. And this is one of the things that can happen is that after for differentiation, in this particular case, you arrive to the same spot. So it goes like this. So processing, once again, not numbers, processing functions. What do you do numbers? What what kind of algebraic operations repeat with numbers that you repeat several times will bring you back to the same number? Well, there are some. For example, you can multiply by -1. If you multiply x by -1, you have negative x, and then you multiply one more time, you have x again. So that's a cycle of two-step cycle, and then you'll keep coming back. Okay, but with functions there is more room to happen. There is, however, the simplest one on the differentiation. The exponential function base e comes back to itself right away. So it's like a stationary point. It doesn't matter how many times you differentiate, it's the same function. Cosine, by the way, also has a full circle. So cosine also make 4 steps. You make 4 differentiations, and you are back to the same function. So exponential, on the other hand, if we take a power function, what's going to happen to a power function? I start with like 1000 power. I differentiate. I'll have 1000 x 999. And differentiate one more time, I have 1000 times 999 times x 998. Okay, so that coefficient in front will be growing. The next one will be 998. But if I keep doing it, where will I end up? It's 0. You will differentiate enough times, you'll hit x with the coefficient, and then you differentiate 2 more times, and then you have 0. So that's a different kind of dynamics that differentiation produces, is with powers. No matter how many times you differentiate, I mean, if you differentiate enough times, you will end up at 0, unlike those two. So polynomials, in that sense, there will be eliminated under enough differentiations. So the notation is, once again, we have Lagrange and Leibniz notation. They are different notations for repeated differentiation. So certainly this looks like maybe just a fun exercise, but really don't forget about the acceleration, which is the second derivative. So the repeated differentiation is important. And so the notation will be, for repeated differentiation, either f double prime, so f prime, first derivative f prime, the next one is f double prime, f triple prime, and then after that you don't want to repeat any 2 more primes, so this is what is written. You write the number of differentiation in parentheses. Okay, so, and on, as many times as it takes. There are functions that are differentiable but not twice differentiable. So we'll also point that out soon. So that is Lagrange notation. Oh, they both start with L. Okay, Lagrange notation.
So on a test,
Yeah.
you might put like
Either one may come up.
find
Oh.
f to the 6, or not to the 6, but
Actually, yeah.
Differentiated.
differentiate 6 times sine x.
Oh, it's not. Yeah. Okay. Well, then if you know, as long as you can explain that, you need to differentiate 4 times, and I mean drop out 4 and differentiate only twice. Right. So if it is I will ask you differentiate 1006 times. Differentiate sine 1006 times, or as you like it. How about 217 times? So the year 2017, differentiate sine 2017 times.
And then we divide it by whatever.
So how do you do it? So sine x differentiated 2017 times. How do you do it?
Differentiate once.
Why? Okay, explain.
Because 2016 divided by 4 gives you a solid round number.
2016 is divisible by 4 apparently. Let me divide. So what is it? 504. Okay. So indeed, indeed 2016 is divisible by 4. So which means that number of times you will make a circle coming back straight to sine. So the only one then remains to be differentiated is 1 time. So it will be simply sine x prime, or it is cosine indeed. Okay, great. Yeah. Okay, so what if you need to differentiate the exponential function 2017 times? Exponential function base e.
It's still the same.
It still be the same, right. And then what if you have x2, or you have a polynomial of degree 2000 and you differentiate it 2017 times? What's the answer?
0.
0. Okay, right. Okay, Leibniz. Leibniz notation. So f from f to d of dx. Then the second derivative is slightly weird. So it is like power goes up, it is a little bit, there is an explanation of the notation that you have in the in this formula, and then like this in derivatives. But especially the denominator, the second derivative can be computed rather than taking two limits. It can be taken with one. And I mean, think about it. If you're talking about how to explain the square in here, why is it squared? Think about acceleration again. What are the units? The units will be, if your location was measured in feet, then, so if these are feet, right, then the units for the velocity will be feet per second, and for acceleration, the second derivative will be feet per second squared. So that's the meaning of that's where the square comes from, roughly speaking. Okay, so, okay, well, there's one more interesting. Also, what's happening if I start with 1x, and start differentiating? What's going to happen? That's a typo.
That'd be to the -2 power, x to the -2, or negative x to the -2.
No, the power, well, it's easier if you write it in the power formula form. Okay, so the power will be actually decreasing, but the absolute value of the power will be decreasing. So the next one will have the power of -3. The formula in front of the coefficient in front of it will be 3. Okay, and then so as you can see, it will alternate the sign to begin with, and then but otherwise there is no end to it. It will be that number will be increasing 1, 2, 3, 4, and so on. Okay, so there is no end to it. Okay, so I guess we're done for today. So I'll assign homework later. Okay.